Okay, so welcome to this session. Everyone, alive now, those on YouTube as well, watching us later. So this session is intermediate between a final session, well, not the final, but another session that Carlos will do next week. And then the mathematics, the formal stuff actually kicks off. So today was just, the idea was just to, to just test the waters, to go through a bit of lightweight motivation, a bit of history, not too much as I initially wanted. So hopefully it will be a very gentle journey for the newbies in particular to see which core mathematical notions in respect to the Hilbert space that you need to pay special attention to, during the mathematics, during the formal stuff that you will go through. And as usually mathematics, one notion is actually built up of several other notions. So this is the thing, the motivation. So, it will be very boring before you get to the important notions, but they are nevertheless very important to understand. So this is the motivation for this session today. And I apologize. I apologize in advance. There are probably typos somewhere, and I will make some comments in physics as well. So Carlos, he's here to correct me if I say anything that doesn't make sense. Okay, I'm sure I will get some thing on the mathematics as well. I hope not, but yeah. So anyway, let's start with what's coming up, the formal stuff. So you will have a review about Hilbert spaces. In our case, complex Hilbert spaces. So it will start very basics of it. You will, go through the basic definition of a vector space. In fact, we'll start with a complex vector space rather than defining an abstract vector space on an abstract field, just to make things go faster. And then, the inner product, this is very important, and so on. And the norm, which is what one of the things that's also important, completeness, this is important. This is one of the features of a Hilbert space. In general, completeness of norm, this is what makes also a Banach spaces. So you'll see the difference between Hilbert spaces and Banach spaces, and you also know that when you get a Hilbert space, you automatically get a Banach space as well. And later on, if you study, you decide to dive deeper, the operators, the bounded operators on Hilbert spaces, they actually form very nice, interesting Banach spaces. But this is like, if you are interested in diving into stuff like operator algebras and all this stuff. Yeah. So this is another motivation for you guys to get this basic stuff, because it will give you machinery to adventure into other things, we'll then go through stuff like other stuff like orthogonality, orthonormality. As you will see, in Carlos's sessions, this will become that you need the orthonormal basis, tensor products, linear functionals, the dual spaces, these things, these notions. And you will also know the thing about the Dirac notation as well, which is justified by this formally, in a formal fashion. This Riesz representation theorem actually makes the Dirac notation make sense. So it gives sense to Dirac notation. But this theorem is also very important, for other things. Classically, for example, the universal approximation theorem of deep neural networks, actually the original proof used this. Part of the proof use this thing here. So it's very important theorem that has a wider applicability across. And then we'll define the operators, the operators acting on Hilbert spaces, blah, blah, blah. In particular, two types of operators, the self-adjoint operators and the unitary operators. In particular, I hope you will see the difference between being a self-adjoint operator and a Hermitian. Physicists normally use the two terms as interchangeable, meaning the same thing. Actually, it's not. For finite dimensional Hilbert spaces, yes, the two coincide. But when you deal with the infinite dimensional Hilbert spaces, as you will see, the two notions are different. A self-adjoint is Hermitian. A Hermitian doesn't need to be a self-adjoint operator. And the reason why physicists need self-adjoint operators is because of they have eigenvalues which are reals in a nutshell. And when you do an experiment, I think our friend Carlos will agree, what you measure is a real number, right? Well, I mean, technically, mathematically, a complex because complex numbers are an extension of real numbers, so they have an embedding. Real numbers are also embedded in complex numbers. So you could also say, yeah, a real number is just a complex number with zero imaginary part. And then we build instruments that can read that. Anyway, so this is the core thing that we'll go the review. Hopefully this will be 3 sessions, but depending on you guys, how the difficulties and these things, it could be we break it in different parts. And another thing is, I don't know what I will actually ask now to see what's the sense in the audience, those who are live now. Do you prefer this to be like in video series, like the review on differential equations, or you prefer live sessions? Who is for live session? Type 1. For video, type 0. Or just say live. Okay. Anyone else have any opinion? Do you want this to be live? Okay. Oh, we put the superposition of both. Maybe half, 50% live, 50% video. Either, okay. Okay. Okay, in that case, this seems like a mixture of things, people, and there is also some others who don't have a preference. So it could be some parts could be video, or we could have videos and then have a Q&A, live Q&A session, something like that to clarify. Yeah. Okay, so we'll think about it. Myself and the people who are actually going to deliver the sessions. It's a nice superficial, nice problem to have, though. So that's good. Okay, so I'll keep you updated. Obviously, next week, Carlos will come back again. Maybe Carlos, I don't know if you want to make any comment next week, if you have an idea what you wanted to go through them, because the week after the mathematical stuff will start.
So yeah, I mean, the idea originally is like we have this like introductory part just to give a context about how these ideas came from quantum mechanics and Hilbert spaces. And the next week, I'm thinking because past week we have a short history about quantum mechanics, and we stop in Schrödinger equation. And I'm thinking like to next week, we have the ideas, how these ideas from quantum mechanics came into quantum computation. The guide is because we could like keep going with quantum mechanics and study like particle physics and all this stuff. But I think this is not important for now for quantum computing. So it's more important if you're a guide from the quantum mechanics, we stop in Schrödinger equation, and then how this came to quantum information and quantum computation. And I mean, next week is these things that I'm thinking to prepare to have, because we give a context how this came to ideas to computation, quantum information, quantum computation, like the things that we saw briefly last week about like Schrödinger equation and the wave function and these things. how this gives a new way, new form, new way to have like a new type of computation. I think this is the idea. And then we will start the math part, and we will not, once we start the math, we will not stop anymore. So we will math every section.
Yeah, one thing I wanted to mention, the advantage of getting rid of the maths now, because this is a course series. This part is about optical models, but there will be another part in like other things, like I guess superconducting and so on. So we will see this is the maths thing done. So what we will do, actually, I think what we should probably do after this course series, this module ends, is to create another separate playlist to put the math sections, including the differential equations review there. So the new people joining up for the other course, so they can have that as a reference. Yeah. For the time being, we just put the maths and the thing in the same playlist. It doesn't make sense to create another playlist for it. But this is it. So if you go through this, we will see, you will have the prerequisite for the thing. We will obviously, as more, the requirement comes in to dive deeper into some whatever stuff as the course series progresses. Maybe we'll come in and add some bits and bobs, these type of things. For example, it could be like someone was commenting on Zulip, whether we will cover unitary groups. Well, maybe not in this thing. We can obviously cover that. In this part, when we define the operators, they define the operators that obviously the unitary operators, they form a group, but that's it. That's about it. And then as the Carlos goes through, if needed, maybe not necessarily in this module, in another module, if there is a group theory needed for that, especially if it's talking about error correction and this type of stuff, then yeah, we'll come back to this again. And you'll probably need to be exposed to Lie groups as well, and also representation theory. So yeah, we'll come back. So, but this will be the basics anyway. So you will have like the baseline, and it will be, very, very good for you to go through the pain of going through this. There's no. This is the thing. The difference between us, because obviously we call the community is called quantum formalism for a reason, is because we don't run away from the maths. A lot of other well-intended courses in quantum information science try to run away because they don't want to put away people because of the maths. But we actually, we encourage people to not be afraid of maths, because it's a very useful tool. All right. So speaking about prerequisites, not just for this thing coming up, but also in general, for our activities, ideally, it's really nice to have people who have taken university level courses in maths, whether they're coming from engineering or some other STEM subject. In particular, they will be exposed to analysis, calculus, linear algebra, even though maybe not the abstract linear algebra, the mathematician style, but still, they get exposed to vector spaces, matrices and this type of stuff. But also another thing that's very nice to have, especially in the context of this review on Hilbert spaces, is a bit of a basics of measure theory. We actually have a playlist on functional analysis and measure theory, of course. So if you look at that, you will get a bit of measure theory on that because of the integrals, the Lebesgue integral, all these things that will show up. So it's nice to have. It doesn't mean that, no one else is welcome, but this will make life easier. If you, even if you forget about it, you have taken this long ago, it would have helped, if you have been exposed to these things, because otherwise it will be very abstract. It will be very, very, it might be very intimidating, so yeah. Another thing I want to say is, actually, this is not a quote. There's a typo here. Could be like advice or something, because I copied, I duplicated the slides, but it doesn't matter. This is meant to be like a tips, not codes. So there's the first typo. So in respect to the mathematics that you are going through, the first advice, I always give, even in the past courses, is that don't resist abstraction. Observe it. Try to feel comfortable with it. Take the red pill, and also take one step at a time approach to abstract concept, because sometimes these things are, very often it is the case that things are built on top of each other. So you need to understand the underpinning notion before you understand the other abstract stuff that's built on top of it. So take your time to put the concept out, and then try to understand piece by piece the main notion. Try to do proofs by yourself before checking other people's proofs. This is very important. It doesn't matter. Don't feel shy. Everyone makes mistakes, but proofs are very important, especially in quantum information science, because you have to do proofs. So it's generally people coming from computer science background or other engineering things. Some people from computer science do like proofs as well, but it's very important to kind of feel comfortable doing manual proofs in particular. I know now you can, there are some tools being built out there that you can automate proof, but yeah, it's always good to be able to do manual proofs as well. If you struggle to understand that concept, try different sources. Sometimes, the same mathematical notion, abstract notion, can be defined equivalently in a number of ways. So maybe a particular way is more difficult for you to understand than another way. So try to do cross-reference your sources and so on. Try set up a study group where you can present proofs to each other. I think George has done a fantastic job with this in our past series. He would organize himself with some other community members like Bob, Berend, and I see some other community members here that were participating in the training, George. And this doesn't have to be online if you are together. I think, George, is it my understanding that you do, in the past, you did have like actual physical get together to go through the materials, right? In a coffee shop or something in Pennsylvania.
Yes, when we're locally in the same place.
Yeah.
And I encourage anybody, if there's more than one of you in your area, to do this.
Yeah. So that's the thing. So this is not codes. This is tips, because you will see I duplicated the slides. The codes I wanted is these ones before we start the Hilbert space tour. This is one from Soskind. I like it. Quantum mechanics is about as abstract as anything can be. Quantum mechanics is about things that your evolutionarily developed neural structure is not prepared to deal with directly. How to deal with it, and then he goes on to say abstract mathematics. It's also true of relativity, but it's worst in quantum mechanics. So I think there is some agreement there. I think that quantum mechanics definitely, compared to general relativity, is a little bit more. There's more friction, especially in the time. Put yourself in the physicist shoes at the start of this the 20th century. When they were coming through, coming across the theory for the first time. Yeah, and then we have this nice quote from Dirac, which is too long to read, but it's also a very very nice one, I think. So this is all to say, the role, how I think. There's a book, I think, or an article or something saying the effectiveness of mathematics in natural sciences or something like that. Yeah. So, was that Wigner or someone who?
Yes, the unreasonable effectiveness of mathematics.
Yeah. So I definitely recommend that also as a motivation to see that it's a very nice tool to have. Obviously, there are the barriers to actually learning it, but it's feasible. It's possible to learn it. You just have to get over it. Okay, so that's the warm-up. Let's see a bit. So as I said at the beginning, I won't be going too much into the history, actually, as I initially planned. But I'm happy to continue if another time or during the actual mathematical courses, the formal part, I can jump in here and there to give something. But today is just a brief thing. So basically, Carlos did a great job in, going through the, the genesis from a physical point of view, from physics point of view, that things that led to the theory of quantum mechanics. All the experiments that he shared with you, showing that classical mechanics, classical physics did not explain these things. So new theory is needed. And these two guys, they were the ones who, them and I would say their collaborators, they came up with two alternatives. I think Carlos mentioned the Schrödinger wave mechanics, which has the notion of a wave function. Yeah, I think he even shared some insights into it, saying that it's the linearity of the function and these things. But basically, this version, so there were two theories. This Schrödinger wave mechanics, which the core notion is the wave function, which encoded the notion of state. And this actually, physicists didn't realize this, but this happens in this, technically, this is the thing, I think the original formulation was using this space, this big space L2 of R3. This also could be generalized to Rn, to arbitrary dimensions. But this is the space of square integrable functions. People in mathematics would say integral in the sense of Lebesgue. Yeah, so we deal with, that's why I was saying, about measure theory, because you deal a lot with the Lebesgue integrals. So this is the thing, the space that formally underpinning his thing, his wave function. This is where this thing was happening. On the other hand, you have the what Heisenberg called matrix mechanics. So this version gave emphasis on observables, so quantities that physicists measure, like the energy and this type of stuff, momentum and all this. But I think, if I'm not mistaken, this is where maybe our friend Carlos here can correct. It didn't use the notion of state, and these he called them matrices, were encoded as operators on this space, this L2 of n. This is mathematically, this is called the space of summable. What's the name for them? The square summable sequences. Yeah, this is the thing. This is the space that underpinning it. This is what he was using in general. In fact, I think he thought he invented new type of mathematics. Heisenberg. He talked to someone. I think it was it Jordan or some other mathematician, to say. Because he was impressed with the, he noticed the operators don't commute, the order, when he multiplied them. So he basically reinvented matrix multiplication. And then the mathematicians basically told him that, in a polite fashion, that this is not, it's not a big deal to mathematicians. They already came across this. But so that was a very humble, a little bit of a humble pie to a giant in physics.
On the other hand, it's remarkable that in this time physicists taught matrix algebra, so he kind of invented it on his own. So credit.
Yeah. Yeah, this is very interesting as well from a historical point of view, because back then, obviously, classical physics, it was mainly tailored to other classical mathematical subjects. Like I think different for general relativity, for example, differential geometry was already a little bit, the classical differential geometry was a little bit advanced enough, thanks to the work of Riemann and all these other people. But we were having in the functional analysis was just getting born. This notion of working with function spaces. These things. Measure theory was also just getting born. So it wasn't really until the second, you will see in a minute. when all these things. That's why by, I don't know, historical accident, the mathematics started to become available at the right time. So, you know, this is the beauty of this thing. It basically gave physicists became the client. They also motivated mathematicians like von Neumann and the others, you know, to help develop this framework. And there were others also like Dirac as well. So it was a couple of years later, I believe, in the early 20s or something, von Neumann, but it wasn't just him. I think there were other people as well, his collaborators. He in particular, he realized that obviously these two spaces have something in common. They are both complex Hilbert spaces. And most importantly, he proposed that the two theories can be unified into one, you know, by basically having, he proposed that the observable that showed up in Heisenberg's theory to be encoded as, you know, self-adjoint operators on a Hilbert space, whereas the Schrodinger wave functions as unit vectors on the same Hilbert space. So that way, you know, the two theories, they have the same underlying mathematical framework. Actually, there is some subtle stuff here I want to mention about this thing of a unit of vectors and these things. In reality, you will come to this later at some point, you know, because of the global phase and these things. Actually, the actual space, if you want it to be more technical, it will be rays. So it's not a thing. So in general, you're actually dealing with the projective Hilbert space. That's the thing. But for our purposes right now, it doesn't matter that. But this is a detail that maybe we'll come back with as you go through the basics first. Okay. For the time being, let's say they are like a unit vectors. Okay, the states, and these spaces are you know, isomorphic, or I will say, you know, unitarily equivalent. You know, in a thing to be more sophisticated, because Hilbert spaces are not just vector spaces, you know. So they carry the unitary, they have unitary representations and all this. So you need to take all that into account. And von Neumann went on to write this book. This is a classic, Mathematical Foundations of Quantum Mechanics. And then Dirac wrote also Quantum Mechanics, the Principles of Quantum Mechanics. And something very interesting about Dirac, I think, I don't know, most of you already know this. When he won the Nobel Prize, he wanted to refuse it because he was very introvert, very shy. He didn't want publicity. And then he was advised, someone I think told him, if you refuse, you will become even, you will gather more publicity actually than accepting it. So he decided to accept it. Because refusing it, he would be the first one at the time to refuse a Nobel Prize. So you could imagine that will generate more publicity for him. So he decided to accept it. But apparently, according to history, he didn't want to take the Nobel Prize because he didn't want publicity. Okay, so let's see. So I'm now going through like what I call a lazy journey with some jargons that people need to know, from the very basics stuff, just as a warm-up. And I will use very toy examples for that, especially for those of you. This is mostly not for those of you who already know most of these things. So, but for the newbies, because I look at the questionnaire, I saw a lot of people never being exposed to Hilbert spaces before on the thing. So I decided to do this. So what's a Hilbert space? Actually, when physicists talk about Hilbert space in the quantum mechanical sense, they mean complex Hilbert spaces. So there are also real Hilbert spaces, okay? So, but this is not what physicists, at least in quantum mechanics, I think there was even an article or a few papers about why, complex Hilbert spaces, why the theory doesn't work with the real Hilbert spaces, but that's another topic, okay? So a Hilbert or a complex Hilbert space is just a vector space with an inner product, but not just any inner product, but an inner product that, has the induced norm complete. So the norm, if you have an inner product, you can get a norm. This is all, don't worry about this, because this is all will come into the actual formal classes, the formal thing that you will go through. Okay, so basically, for those who are mathematical a little bit more, this actually telling us that a Hilbert space is a complex Banach space in respect to the norm. So basically, when you have a Hilbert space, you also automatically get a free Banach space, basically. But the converse is not true. Huh? A Banach space doesn't need to be a Hilbert space, okay? Okay, so complex Hilbert spaces are the underpinning mathematical, the core, I would say the core mathematical structure used to model quantum mechanical system. Now, there are other structures that you can build, like operate, like, on the algebraic formalism, for example. I think it's called the density matrix formalism or whatever. That you use like a C-star algebras, behind scenes. This is something, another advantage that you have in taking this course, because this will give you the basics to go and study operator algebras, and C-star algebras are just examples, canonical examples of those. Okay, so yeah, so here's an example, a lazy example, two lazy examples. One is a very two-dimensional, like C2. This is everyone who have taken Qiskit, or have read the Qiskit test book. Have seen this, okay? And obviously, this generalizes Cn, for any n, greater than, than or equal to 1. This can generalize, But for quantum computing purposes, you don't actually want any n. What you want is n to be equals to 2 to the k, where the k is the number of qubits that you want to, you have under consideration. Okay, so this is the thing. So here's a very simple. So you will understand later, for those of you new to this, why this is a Hilbert space. This is a complex Hilbert space. These two. Okay, obviously this is a special case of this. Okay, so that's the first jargon, a Hilbert space. So when physicists say Hilbert space in the context of quantum, what they mean is actually, to be more precise, a complex Hilbert space. Okay. The second jargon, state vectors. This is where our friend Carlos actually I'll ask him in a minute. So state vectors. So given a complex Hilbert space, state vectors encode the notion of state of the physical system that you have under consideration. And I believe this is called pure state. Is that correct, Carlos? This is what physicists call pure. Yeah, Carlos will, in his classes, he will explain what this means. Okay, we don't need to jump the gun. Okay, so so they meant to encode, again, Carlos, please correct me in this. These meant to encode as much as information about the state of a system at a given time. Obviously, in quantum computing, the qubits are actually the state vectors. And also, for just a small note here, I've seen, for convenience, physicists often require that the vectors to be normalized. That's why I was using the term unit vector, okay? For convenience, okay? For, I guess, doing calculations and some other stuff that will become obvious as you go through the postulates of quantum mechanics and going through this stuff with Carlos. You will see this. So here's a toy example. So in this case, we have the Hilbert space like C2. I believe this is a valid state. Now, would this is where Carlos can come in. Which system could this be a possible state for? Is it a spin 1/2 system? Something like that? It looks like. So yeah, but again, this is something that you can tell me later if okay, someone is there a message?
What is the exact difference between the two spaces?
Which spaces? Let's go back. You mean these two examples? You mean these two? Well, obviously, this one is a special case of this. I'm just generalizing to this, so I could make this note here. So I could have just used this one. Obviously, this is C2 is a special case of CN is just
Banach versus Hilbert is the question.
Okay. This is something. Okay. Well, this is something that I invite you. You need to attend. Okay. Oh, whoa. We are going to the top. I think I clicked somewhere. This is something that you need to come to the functional analysis, to the math courses. You will see the difference. Yeah. But a Banach space, in a Banach, you don't require an inner product. Basically, you work with norms. That's it. Yeah, so you don't, but it's very, very, very often you have. This is something I don't want to jump the gun, but you will come to it in the math classes. There are Banach spaces with norms that you cannot actually construct. You can't construct an inner product out of them. Okay, so that's why a Banach space doesn't. But with a Hilbert space, because it's a norm, it's an inner product. It has an inner product. You can construct a norm. You can always construct a norm out of it. Okay, so that's the same. But you need to come. That's a very, very good question. Yeah.
We have another question from Claudia. Can we have a mixed state expressed as a vector state, or only the pure states can be expressed with vector states?
I think this is probably a question to keep it in Carlos's thing. It's very interesting question, but this is a question to the thing in the more pertinent to the physics thing. Yeah, because remember, this is this thing of thing. It's not just the mathematics. At the end of the day, there was one quote actually. I don't know who said this, saying that. Quantum states don't live in a Hilbert space. They are in a lab. So, whatever the quantum state you come up with on a Hilbert space, whatever construction you make, at the end of the day, you need to have, be able to create it in a lab. Okay. So, yeah. So you need always to take into account, the experimental setup. I think our friends like Carlos, for example, if they wanted to model a physical system, they would obviously analyze the system and pick the proper Hilbert space, and then they would pick the state carefully, okay, very careful, and then they will pick their whatever, say for example they wanted to do something with the Hamiltonian, they would pick a suitable operator and maybe go to the experimentalist to say, okay, this is what I want. Can you do this in a lab? Am I saying BS, or is it more or less like this? The interaction between a theorist and an experimentalist, Carlos. How would you go about if you have a theory thing and he want to interact with the experimentalist?
Yeah, the first thing is asking him if is something absurd here in our proposal. Sometimes I talk with I have some works, and I talk with the experimentalist guys, and is something absurd here first of all, or is something that you can do in the lab? So
yeah.
Because in general, we have some proposal, but it's not ready to do the things in the lab yet, because there are some difficulties in the experimental part, and sometimes the theoretical proposal is not adequate, something like this.
And there's a comment. So I guess basically because quantum mechanics requires linearity, you have to use Hilbert space. Thanks.
Well, maybe there is a truth to it. I will let Carlos reply in a minute. But linearity by itself is not the thing, because you could why Hilbert space is just one of the many type of vector spaces that are out there, right? Yeah. Yeah. But I guess Carlos already answered this before through the example of this Schrodinger equation, right? The wave function, that he shared. Yeah. So yeah, the linearity there, yes, it means that you need a linear space. Yeah, that's it. But with Hilbert space, I guess it was one of those things that it just became like the suitable mathematics that could.
what I understand for the physical part is because, I mean, people notice that the wave function is complex. So by that time, it's not usual. I mean, you work with exactly complex things. So I mean, at least for the physical part, I understand that you need linearity, yes, but the things that you're working now is complex. So let's say the matrices you're working has complex parts. That, I mean, that's why you don't have like a physical meaning for the wave equation. So what the wave equation means is like a amplitude probability, and not, but it cannot be measured exactly. So I think I don't understand well also, I think, why Hilbert space in this case, but what I understand from the physical part is because, I mean, you need linearity and need to be a complex space.
Yeah. And in this case of the justification, at least from a mathematical standpoint, the what Heisenberg and Schrödinger use, I guess you would say that they naturally led to Hilbert spaces, because the space of the object that they are dealing with, it's have the natural Hilbert space structure. In the case of Schrödinger, for example, using the space of square integrable, that's where his wave function lives formally. So yeah, but it's very interesting. Yeah.
I would just mention that a Banach space is linear, so you can add. But what makes a Hilbert space special is the inner product actually gives you this notion of orthogonality, right angles, and then that actually gives you angles and rotations in general.
Yeah. You will get to this as well in the more formal thing. That's why I'm saying. Thanks, George. Yeah.
When we talk about the postulates of quantum mechanics, I think we'll have some discussion. I mean, the importance of orthogonality is because it's related with the probability to measure. So the probability to measure something is 1. I mean, if you make an experiment and you measure, so the probability must be 1, because it's one thing that you measure. So that's the physical reason, that the main physical reason, because of the orthogonality. But this we will discuss later in the postulates.
Yeah.
After we have this math background.
Yeah. Okay, so yeah, so going back, so this is what state vectors, and as Carlos nicely put it, and they also decode from I don't know which physicist said this, that as quantum state lives in a lab, the mathematics is just there as a guidance. At the end of the day, it has to be something that's feasible for people to do on a lab and extract results from the experimentation. All right, so let's see. The second jargon, superposition. This is also for the newbies, for those of you. I hope I didn't make any typos again. But this is basically, in a nutshell, again, a lazy explanation, a linear combination of state vectors involving countable orthonormal bases. So here's an example here. These two bases, for those of you who have read Kisket, you will notice these two, they are also known as the computational basis. Yeah, these are orthonormal in the sense of, like Carlos was saying about inner product, for example, the inner product with these two is 0, and they are normalized as well. Their norm, if you take the norm, is 1. Okay, that's why it's called orthonormal. Now, countable, this is one of the mathematical subtleties. Again, you will go into this more. It's just it's something that you probably don't need to mention, because a lot of the Hilbert spaces that you actually need, physicists already came up with them. So you don't need to construct any new one. But it's just one of those subtle stuff that actually in reality, very often what physicists actually need, because of this countability thing, is something called separable Hilbert spaces. These have the bases are countable. Well, this one, for example, obviously this is finite dimensional Hilbert space, so it's countable, which means that the basis elements, you can, the set of the basis, you can put them in bijection with the subset of the natural numbers, right? So, but there are Hilbert spaces that don't have countable bases. So the bases are not countable. You can't. So these are very wild use cases. So in reality, this is separable Hilbert spaces like these guys, and the ones that you will encounter. They are the ones that you want. They are the ones that, so the orthonormal basis of those ones are the ones that you want. Okay. Here's an example of a superposition. It's just a linear combination. Okay. So, I have the basis. I've chosen my orthonormal basis. In this case, I happen to be the 0 state and so on. Or, if you are coming from quantum computation, they call this the computational basis. And then I've written this. And I get this. I hope I got it right. I didn't make any typo. It would be nice if you can spot any typo there. Yeah, but maybe Carlos, you can mention briefly the importance of superposition, in connection with the interference. I know you will go through all this stuff later in more details during your the physics part during your course.
Yeah, in this case, I think in quantum computing, the superposition, you have a state like that. I think is important because you can make a type of parallelism, right?
Mm-hmm.
I think this is the most, I don't know, the most important, one of the most important things, the advantage for quantum computing than classical computing, because you have this natural parallelism that can appear, and if you increase the number of qubits, in this case you have 2, but if you increase the number of qubits, you have 1 in this case. But if you increase the number, you can have more parallelisms 2 to the n, to the decay that you are using. The possibilities. So I think for the quantum computation, this is really important. A very big advantage compared with classical computing.
Yeah, so thank you. So so obviously you have seen an example with this in a very simple example, this toy stuff with the thing. Obviously in the course you will come across more complicated spaces, but you still need notion. So all to know is it's a linear combination, there's nothing else. Mathematically it's just a linear combination, but it's a linear combination involving an orthonormal basis, basically. Okay, the other one is this one is harder because it's harder to we don't know, we haven't defined a tensor product. You will learn what a tensor product is during the course. So this is entangled states. So in the lazy explanation, these are states in the product space. Let's call them H1 tensor H2. Of 2 composite systems, S1 and S2. Okay, so let me pause and explain here. So in quantum mechanics, okay, let me go back to classical. Carlos, please correct me again if I'm saying nonsense. So in classical mechanics or in classical physics, when you have, say, two systems, system 1, S1 and S2, they are normally, their phase space is normally, say, something like a symplectic manifold or something, if you are doing Hamiltonian mechanics, something like that. If you want to study the 2 systems together, all you do is to take the Cartesian product of these 2 spaces. Yeah. And then obviously by taking the Cartesian product, you can have the state of an individual system here, S1, the state of the individual system on the thing as pairs. Okay. But in quantum, it's not what happens. When you have 2 systems, let's say system 1 and system 2, and you have their respective Hilbert spaces. By the way, in principle, these 2 Hilbert spaces can be the same Hilbert space, okay? It could be, C2 itself, tensored twice, okay? So you take the tensor product of them, okay? So the way the tensor product, I won't define it here. This is why it was a bit of a tricky thing to include this, because we haven't defined tensor product yet, but you will get the idea. The core is to give you the idea, and then, you will pay attention how the tensor product is actually constructed for you to see this. So the idea is that entangled states are states that cannot be written like this. So you cannot find individual like two vectors in one in H1, the other one in H2, so that so you cannot find a vector in the whole, in the tensor product, in the total space, that can be written as under this composition. So it's a tensor of it's a tensor product of two individual states from the respective systems. So these states are called entangled. Here's an example. So in this case, suppose we have two systems S1. Let's suppose they are both using C2 as their Hilbert space, okay? So the tensor product of Hilbert space of C2 as C2, this is actually isomorphic to C4, because the dimension of this, you will learn the dimension of the tensor product in a thing. But this is dimension is 4, because it's 2 times 4. And you learn in linear algebra 101, you know, vector spaces of the same dimension are isomorphic, okay, in finite dimensional case, okay? So in this case, the tensor product space is actually C4. And then we have this vector here, this vector in C4. This is, I would say this is entangled because there are no vectors in C2, no two vectors in C2, so that, you know, when you take, there's a typo here, it shouldn't be a thing here, I will correct this, so that when you take the tensor product of these two in C, it will give you this, okay? So the quantum computing guys, this is the thing. I believe there's a special name for this. Is it a Bell state or something like that? This is called, yeah. So this is basically what entangled or entanglement is really this amazing feature that you have this space, the tensor product space. There are elements of the tensor product that you cannot construct through you know, direct tensor like this. This is the thing. Yeah, Bell state, yeah. So yeah, so this is a jargon. Entangled state, you know, the underpinning mathematics is really the tensor product. You know, you will learn what tensor product is. By the way, there is tensor product of the actual vectors, but there is also, obviously, there's tensor. You can also tensor the operators themselves. This is something that you will do also in the thing, in the mathematical review. Okay. The other jargon, now we are coming to the operators. As I said before, self-adjoint operator, this is a special type of linear operator. Operator is just map, okay? We use the term operator because it's fancier, you know, than say map. So this is just a linear map. And now there's another jargon here, which I was trying to avoid, which is this thing of called spectrum, okay? So in a nutshell, spectrum, let's take in a finite dimensional Hilbert space or vector space in general, is the set of eigenvalues, okay, of the operators. In this case, self-adjoint operators, they have like real, the eigenvalues are real. So that's why the physicists, they I guess the natural thing for them to use self-adjoint operators. And this is the thing that I was also mentioning. Physicists don't use, they normally say Hermitian operator. This is okay when you deal with finite dimensional Hilbert spaces, but mathematically, this is not quite correct, because you know, in infinite dimensional Hilbert space, these two notions don't coincide. You know, a self-adjoint operator is a Hermitian, but a Hermitian doesn't need to be a self-adjoint operator. Okay, so you will see this. I will ask the mathematicians to show a difference between the two notions in when you deal with when you come with examples of infinite dimensional Hilbert spaces for you to see this. But physicists, so just insert in your mind when they mean Hermitian, especially if you are coming from mathematics, they mean self-adjoint, okay? Because they want real the eigenvalue stuff, and you know, to be on the thing on the real line. And I won't even tell about, you know, the difference. This is something that you will come to, I guess, at some point in Carlos's course, with operators that have continuous. The spectrum is not discrete; it's continuous. You know, the so-called unbounded operators as well. These complicated stuff. You know, but yeah, here's an example. These are Hermitian, or because we are in finite dimensional, so maybe we don't need to use the term self-adjoint. But I claim these are Hermitian, and I guess there is also a name for this. They are called the Pauli matrices, I guess. This is the thing. So they are a prototype of this. Okay, so that's another jargon that you need. The only difference here with this, you will in your mathematical review, you will deal with them. You will see very strange looking operators with integrals and all this stuff, because you are dealing with infinite dimensional Hilbert spaces, so it becomes more complicated. Yeah, but it's the same notion. Okay, jargon number 6, unitary operators. Okay. So the unitary operators, these are the operators that preserve the inner product and thus the induced norm. Okay, so they are the isometries, of the space. Okay, you will again come to this, and something very interesting is unitary operators. They form a group, generally a non-abelian group. Okay, and if you ever wondered why quantum computation is reversible, is precisely because of the group structure, right? You apply the thing. If a quantum computation is applying a gate, a unitary operator, you apply it. If you want to undo it, just apply the inverse of the unitary operator. Then you have the thing. You go back to where you started. You undo the computation. So this is because of the group structure of the unitary operators. Okay. So they play a very important role in Teng and also in quantum, because that's why you hear physicists, right, Carlos, you say the evolution is unitary, but provided the system is not disturbed, right? So the system evolves. I guess you will see this in the axioms. I don't know if Carlos wants to make an extra comment on this, that provided you don't disturb the system, it's isolated, it evolves unitarily, and then you try to do something, it interacts with outside. Anyway, this is something that Carlos will talk to you about. All right, so I think that's it. So these are the core notion, even though we've been using finite dimensional Hilbert spaces to show the example, but these are the basic things that you need. You need to make sure that you understand in your course. That's it. If you know this, you will be fine. Anything, obviously, to know these, each of these jargons, they require other stuff to be in order to be defined. So you need to go through the pain of that. But in essence, this is what these are the fundamental notions the basic notions that you need going forward with the thing. Especially in the context of quantum computing, basically. So with that. Just a reminder that I'll upload this on GitHub, this slide. You can join us on Zulip. I haven't put the Zulip only because it's only invite only, those who are actually taking the course. If you want to join the course, just reach out to us and we'll add you on the thing on the Zulip. Yeah, that's it. This is the thing. The quick lazy journey, and I'm happy to come back again, especially I guess once the actual mathematics start, maybe I can show up to whatever, and even as the course is also progressing, maybe there will be some opportunity for me to come in and do something. And we will also, Carlos and I were planning to invite guest lecturers as well. To come in and give a talk and these things. So there are a lot of exciting stuff to go. So it's not just, you will go through the pain of learning all this, especially the mathematics. But, at the end of the day, it will be worth it. So now I'll stop sharing. And then if you have any questions for me or maybe for Carlos, especially in respect to the physics stuff, you can feel free to ask. Anyone wants any questions or any comment? I can actually, if you prefer, I will actually stop recording, and then anybody who wants to, feel free. I will stop recording now to give people opportunity to come on board. So